Hello everyone and welcome to our 12th lesson, the radical functions, or as they're also known, root functions. So we're already at lesson 12, over 1/3 of the way done with our math chapter, and yeah, let's get started with the lesson. Radical or root functions are those that have x under a root, or raised to an exponent, in fraction form. This means that today we finally learn a bit about the roots, rationalizing denominators and simplifying slightly harder roots. The general formula is nth root of x to the power of p, or x to the power of p over n. So if you want to convert from the root or the radical form, you write it as such. So the exponent stays in the numerator, and the power or the index of the root stays in the denominator of the exponent. It is also important to note where the numerator is placed and how it is placed there, as you can quickly get from real numbers to complex. So always make sure that you check if the negative sign is present within the brackets if x were to be negative. Also, the outcome of a root will, if it's an even indexed root, will always be positive. So when you take a root of something, it is positive if n is an even number, so 2, 4, 6, 8, etc. N is called the index, and p is the exponent. I will probably be using the phrase power of the root as index. In my language, we didn't use index, we just used the degree of the root. That's a rough translation. So I'll be using index and power of the root, whichever one you hear me say. I'm referring to this one right here. Hopefully this clears out the technical problems about writing it. So this is how a square root would look like. So p is equal to 1 and n is equal to 2. Another way of writing square roots is without the index completely. So anytime you would have an index or power of the root 2, you can just omit it. And this also means the square root of something. Both notations are correct and mean the exact same thing, so it's up to you whichever one you prefer to use. This one is easier, especially in harder equations, but for the easy level that we're working on, both are fine. And this is a cube root, so n equals 3 and p is 1. And I forgot to add the second parts where I write them as square root of x being x to the power of 1 over 2 and cube root to x to the power of 1 over 3, but you get the idea. And here we have an example where we have a cube root of x squared, so that's how it would look like. In the real numbers, the even roots, so n being 2, 4, 6, 8, etc., so the even roots of negative numbers are undefined. For instance, square root of -4 has no real solution. However, odd roots, so 1, 3, 5, 7, 9, etc., work for negatives, like cube root of -8 would be -2. Now let's ask ourselves, what would the domains of our radical functions be? Turns out the answer can be easily represented by groups, just like with power functions, so by odd and even power of the root, or index. Here we see that the domain of square root of x is x greater than or equal to 0. Which, if we remember from our last lesson, the inverse functions, makes sense, as that is the inverse of the x squared function, and where we swapped the variables for the function itself, we also had to switch it for the conditions. So it would make sense that the same thing happens for the domain and range, sort of. Meaning, since before we had y is greater than or equal to 0 for the range, now that becomes the domain of this function. So the range of x squared was greater than or equal to 0. Now that changes into the domain, because domain references x and range references y. For cube root, our domain is all real numbers. So we can try for other indexes or powers of the root, and we will always get the same rule like we have right here, meaning that we can generalize it. Only when we don't move the function, because when we do, we also have to adjust the domains and ranges and everything. But yes, when the index is even, so the power of root is 2, 4, 6, 8, etc., the domain is x is greater than or equal to 0, and when the index is odd, so 1, 3, 5, 7, 9, the domain is all real numbers. Now, since I haven't officially presented roots, Or did I? I didn't. It is time I do a short introduction. So we know that when you multiply numbers, you get a certain, usually other number. Because if you multiply 1 with 1, you get 1. And 0 with 0 is 0. But to turn this around, you would divide. But if we want to find out if there is more of the same numbers that when multiplied give us this number, we take a root of it. Most of the time it's about remembering the squares of numbers, but you can also find n numbers, which equals n being the power of the root or index, that when multiplied give us the wanted number. Then just try to get them as close to each other as possible. For instance, let's try it on 12. I know that 6 times 2 is 12, but are there any two other numbers that are closer together? Yes, 3 and 4. Okay, and since these are as close as I can get them, I know that the square root would be somewhere between them. It is possible to predict rough values like 1 or 2 decimals with some methods, but I won't bother you with them. You're also more than welcome to learn them on your own, as I personally think that knowing how to do roots in your head, like solve radicals, is actually a very cool skill. This is how we would write it, so a to the power of n is y, nth root of y is a. So time for some helpful properties that can help us solve these problems. As we know that fraction exponent is basically a compact way of writing a root, and this can help us a lot. So the rules of exponents still apply here, so it's easier to work with them. Then we know that we can multiply both the index and the power with the same number, just like with normal fractions. So we multiply both with k, for instance, I would have x to the power of 2/3. I can multiply both with 5, and I would have x to the power of 10/15. That's also possible. Next up is that when we multiply two numbers under different roots, or with different exponents, the exponents are added together. So as long as the base is the same, we can add the exponents together. So something like this. This is where this rule comes handy, because you extend the fraction so they have the same denominator. So we would have to like multiply this one with m and this one with n, and that's how you would add them. And probably the last property, that we can break apart the exponents. So if we were, for instance, to have 3 to the power of 7 over 2, which I'll solve later, you can find the sum in the numerator and then break it apart like so. So 7 is a sum of 3 and 4. So let's break it apart by this rule. 3 to the power of 4 over 2 times 3 to the power of 3 over 2. Why does this work? Well, because of the property. If we just ignore the divided by 2 in the exponents, 3 to the power of 7 is 3 to the power of 4 times 3 to the power of 3, because you add them together. Now we add the denominators, and since they are the same, we can do the addition again. If they were different, we would just have to use this second rule here to get the same or common denominator and then add them together. This right here would be 3 squared times 3 to the power of 3 over 2, and this would be 9 times square root of 3 cubed, or square root of, I think that's 27. That should be 27, yes. You can leave it as the square root of 3 to the power of 3, or write it as a square root of 27, whichever your teachers prefer. Both are correct. I think this one is slightly more elegant as well. Now, for our first example, we need to evaluate the value, that's a funny phrase, of square root of 36. So we will break 36 into prime factors. They are 2, so basically I'm gonna be dividing by primes and just noting them down, and then what's left, keep dividing that. So 36 divided by 2 is 18, then divide by 2 again is 9, and 9 is 3 times 3. Okay, so we have our primes written out. Then we combine by the same base, so we raise them to exponents. So 2 times 2 is 2 to the power of 2, and 3 times 3 is 3 to the power of 2. Now, since we have the root, we can take a root of each one individually, because multiplication, that's the basic property. So this rewritten would be 2 to the power of 2 over 2 times 3 to the power of 2 over 2. And since we can separate that, we can also separate roots. So technically I could rewrite this square root of 2 squared times square root of 3 squared. But we get 2 times 3, which equals 6. This is our final answer, which is the square root of 36. For next example, we have a cube root of minus 64. Since the index is odd, we can have negative numbers under the root. So I will be separating the factors. So the first one I notice is minus 1, so I can get rid of the minus sign. I write minus here, and then I keep writing down the primes. So 64 divided by 2 is 32, divided by 2 is 16, by 2 is 8, by 2 is 4, by 2 is 2, by 2 is 1. So when I multiply them all together, I get minus 64. We rewrite this to the exponent, and we get minus bracket 2 to the power of 6, end of bracket, all under the cubic root. I could avoid the center brackets because this 6 would always not be over this, unless I would put the 6 over the outer bracket, but again, complications. So let's rewrite this in the form of x to the power of 6 over 3 and see if the negative sign is under the sign or outside of the sign. So first is x to the power of 6. We see that 2 does not have the minus sign on it when the power of 6 is applied. However, the 3 does. But since here the exponent is the one that matters, we can ignore, if this minus sign was outside or inside, it would not matter. The result would be the same. That's how we know it's an even, this is the odd function, because as we remember the rule, if you put in the negative value and the output is negative, then you have an odd function. If you put in the negative input and you get a positive output, that is an even function. So here, since we put in minus and we get minus outside, this thing does not encompass the minus sign, so we would write this as minus 2 to the power of 6 over 3, which when we cancel out the 3, we get minus 2 to the power of 2, which is minus 4. So we see that it is very important how our brackets are placed and how our exponents are determined. As for graphing, here is a set basic table for graphing with square roots. I picked the first 4 square numbers, which are 0, 1, 4, and 9, and I wrote the corresponding y values. So the root of 1 is 1, the root of 0 is 0, the root of 4 is 2, and the root of 9 is 3. Basic square root graph starts at the origin and increases normally, but the greater the x, the slower the y increment is. I think that's correct. Correctly worded, yeah. But it never approaches a specific value or stops rising, so we do not have an asymptote. It just keeps on going up, just slightly slower. Sadly, I couldn't manage to get the graph all the way to x equals 9, while still preserving the fast rising here at s is almost 0 visible. But I hope you can see the vision, and if you graph it, you can also see it for yourself. Now for the cube root, we see that we need to increase x by a lot to get the same y values. And here we have all real numbers in the domain and range. So they cross through the origin, are symmetrical, just like the odd power functions were. So over the origin symmetry, and they contain negative x's and negative y's. And you can see that the rising near 0 is even more steep, but then it starts to fall a lot faster, and it's like, it slows down much more than the square root. If I said like the root with index of 1000, so the power of root is over 1000, it would almost look like a straight line here, straight line up, straight line right. You can graph it for yourself. It's hilarious to observe graphs in the extremes. You may even be inspired to do math, who knows? But yes, let's talk transformations. When we add something to the x, we move graph to the left, and when we add it to the y, we move it up. But does that stay the same for radical functions too? Let's see the comparison. So on the right, I'll have the normal radical function of square root of x, and on the left, I will have the square root of x minus 4, then on top of that, plus 2. So the shift would be on the y-axis as plus 2, and on the x-axis as minus 4. And here we can see the graph is indeed moved 4 to the right and 2 up. Stretches also work the same way, but yeah, you can check out the stretches and shifts as well for yourself. I'm just telling you, they work. They have no reason not to. We did it for all functions previously, so it would make sense that this as another function would follow the rule. Next up, we will be simplifying radicals. As we know, we can do it one way by finding all prime factors and taking the root of those. So let's try this. If it works, it works. We can break 72 in 2 times 36, which is 2 times 6 times 6. So we remember that 6 times 6 is a square, and if we take a root of that, we have 6. So 6 times square root of 2 is the answer. Nothing too complicated, hopefully. But brace yourself, because this example consists of multiple roots, And here's a square root over a fourth root of 8 multiplied by a cube root of 4. Yes, I'm aware that this looks daunting, but don't worry, it is not as hard as it may look. You'll see. So, first we rewrite the roots as exponents and the values as primes to some exponent. So, 8 is 2 to the power of 3, and 4 is 2 to the power of 2. The square root is everything to the power of 1 over 2. Next, we rewrite the remaining roots. So, the fourth root would be over 4, so 2 to the power of 3 over 4. And the third root, so cubic root, would be 2 to the power of 2 over 3. Now, we can combine these. So, we add together the exponents. 3/4 plus 2/3. We can multiply the first one with 3. So we would have 9/12. God damn, I can't speak. And the second fraction with 4. So we would get 8/12. Damn, I can't say 12. But anyway, 8 plus 9 is 17. So we would have 17/12 to the power of 1 over 2. And since this is multiplied to this exponent at the end, we multiply it by 1/2, which then is multiplied in the bottom of the fraction line, which gives us 17 over 24. This 24 becomes the index or the power of the root, and 17 stays as the exponent to 2. Not the prettiest result, but a good one to learn from. And what we learned is that different roots inside one radical can be handled by converting to exponents, combining, then applying the outer root, and then reshaping it as one normal one. For instance, so if they added up to 24, if they added up to 24, we would be able to cancel it out and we would just have the result of 2. But it didn't, so we do what we can. Now, when we have radicals in our fractions, so a fraction, top of the line, bottom of the line, and then we have a radical, we can have them in one of two places. First one is numerators, where we like it, we don't mind it. And then we have denominators, where mathematicians absolutely hate it. Because, well, it looks better and simpler if you put it in the numerator. So how do we solve this? For simple fractions, where there's only one term, we simply multiply both sides by the fraction, both sides of the fraction line with that radical, as that would cancel it out, leaving us with the value under the root sign outside of it. But let's see this on the example. So we have 5 divided by square root of 7, and as we said, we will multiply both sides with square root of 7. So we have 5 times square root of 7 divided by square root of 7 squared. Now we cancel out the root in the bottom, and we get 5 times square root of 7 over 7. This is our result. Another way is when we have a binomial in our denominator. That is when we multiply by its conjugate. If you don't know what a conjugate is, it's when we have a binomial relation like a plus b. Its conjugate would be if we change the sign in front of b, so we would get a minus b. What we get is, if you remember back, the difference of squares, when we had something like a plus b times a minus b, and the result ended up being the squared a minus the squared b. Same things apply here. We will cover conjugates more in the lesson about complex numbers. I don't know if that's actually the next one or in a few ones, but I will spare you the details and complexizations. Is that an English word? Probably not. For now. And for now, it's enough to solve our second example with this formula. Yes. We're dividing 3 with the difference between 2 and the square root of 5. So the conjugate of this would be 2 plus square root of 5. So let's multiply both sides by it. We see that on top we would have 6 plus 3 times square root of 5. And on the bottom we would have 4 minus 5, because 5 squared under the square root was 5. And 4 minus 5 is minus 1, and this is our result. This was all for the lesson on radicals and roots. Here is the mini test. Hopefully everything goes well for you. This lesson is again a lot shorter. I have exams, well, had one today. For you, that's like yesterday. Is it? It is, yeah. Yeah, as you see, I stopped streaming because university hits again. And yeah, I go to Japan in September, so I'll probably have one upload coming up slightly late. I'll try to make the video beforehand, but that means I have to make 3 videos in a span of 1 week or a week and a half, which is going to be a lot for me, but I'll try my best for you guys. But yes, I hope your mini test solving went well. The solutions are already up and they're linked to in the top right corner. And I'll see you all on our next quest. Bye!